I came to most of the people were on India.
These online is nice. You can just look really closely at your phone. It resolved all the people tend to
Take screenshots.
all these panels, so you can't see the.
And maybe we can start now. So, good afternoon, everyone. Welcome to this week's HAO Colloquium. And today our speaker is Ritesh Patel from Southwest Research Institute. And Dr. Patel is a research scientist at the Southwest Research Institute, and he completed his PhD in astronomical instrumentation from the India Institute of Astrophysics, Bangalore, under a joint program with the University of Calcutta. His key areas of research involves around the phenomenon of magnetic reconnection at small and large scales, exploring the solar middle corona region and white light polarimetry. He had been involved in India's first space-based solar mission, Aditya L1, and now working at Southwest Research Institute in the Science Operations Center of NASA's recently launched mission Punch. And today, Dr. Patel will be talking about Parker Solar Probe flies through an eruption-associated magnetic reconnection carbon sheet in the solar corona. And please go ahead.
Thank you, Zia. And as Zia already mentioned, I'm more interested in magnetic reconnection, and this talk revolves around one of such recent encounters and really a novel observation by Parker Solar Probe. And as you can see that we have a big team who has contributed a lot in this project. So I will directly jump into what magnetic reconnection is. I know everyone in this room are aware about this fundamental phenomena in MHDs and plasma. But for completeness, as we know that whenever there is a gradient in magnetic field from say positive to negative, we get current sheet, and during certain circumstances in this idealized or the plasma conditions, we get reconnection where the topology changes and reorient, and hence the name suggests reconnection. And there have been a lot of remote sensing observations in the past about different manifestations of reconnection, whether it's current sheet, plasma blobs, or supraarcade downflows, and also jets. So we have been observing this phenomena from ground-based and space-based observations at various wavelength regimes. And theoretically, this idea was pursued in early 50s by the two gentlemen, which we all know, Peter Sweet and Eugene Parker. And based on their name, we had this famous Sweet-Parker model shown on the left. Though there were certain limitations, but it was a good starting point on explaining how the solar flares are happening and how this reconnection progresses. I sometimes wonder if we had these two gentlemen in the present generation, we could have also named it Spider-Man model. But jokes aside, we moved further from Sweet-Parker model to Petrick model, where the diffusion region was narrowed down, and there were proposals of slow mode shocks. And this is what we see in the solar observations. So we know from all the way large scale flows, CMEs, and flares that we have been monitoring over last many decades now with EUV and even X-rays. So what we are observing here is the background EUV wavelengths, and the flickering red glows that you see is from the X-ray RESI observations. And you can see whenever a CME happens, all sorts of these energetic phenomena, energetic particle hits also take place. And underlying all these phenomena, we know that there is magnetic reconnection that's driving not only the flares, but CMEs, and also accelerating particle. So in a way, we can say that magnetic reconnection is a very efficient energy conversion mechanism where the magnetic energy that's stored in these twisted field lines get transferred to other forms of energy like electromagnetic radiation or particle acceleration, and even mass acceleration like CMEs. Not only sun, we also see this reconnection phenomena in other places in our in Earth-based phenomena like laboratory experiments or even Earth's magnetosphere, where one of the first discoveries of small-scale reconnection in situ measurements were made with some instruments like MMS and TEMIS earlier. And talking about astrophysical scales, we now know that even there are X-ray flares in pulsars, and then galactic nuclei jets have been explained based on this reconnection theory. And also, we since we have some space probes that have crossed heliopause, so we know how the turbulent and unstable phenomena occur in this edge of the heliosphere, and not only Earth's magnetosphere but other planets like Venus and Mars. There also this kind of reconnection phenomena have been observed. So this is like a application in large astrophysical to even lab-based plasma scales. That's why to understand, to know more about this phenomena, both from, say, observations, modeling, and experimental perspective, becomes important. From the modeling perspective, people have tried to explain different sorts of instabilities. Like in this example, you can see the current sheet is expanding, and at the same time, different magnetic islands are being created, giving this sort of topology where we can see multiple X and O points. And this is one of my favorite regime where you can get fast bursty reconnection, and that too in very quick time, and all happens in a small region of current sheet, which is very thin. In this direction, we have also many observations, especially the one that I'm showing an example from September 2017. This particular current sheet was observed in many different wavelengths, or ranging all the way from white light to UV, and even in IR, including the comp observations. An interesting part of this particular event was that you can see most of the phenomena that we associate, like CMEs, current sheet down here, plasma blobs, and particle acceleration. And interestingly, there were, I think, over 100 research papers on just this event so far, all because of the vast data set that was available for this particular event. And obviously, its orientation is in such a way that we can observe the thin current sheet along with the blobs all the way going bidirectional. So to give a context about the bidirectional flows, this is for the same September 2017 current sheet event. You can see as the movie is progressing in the distance time plot on the right, you can see the contemporary downflows and upflows pairs that are getting highlighted as the time progresses. So this was like long-lasting event that was seen earlier, where you have clear evidence of bidirectional flows, though it's not the only one present, but this was very well observed. That's why I wanted to highlight this particular event.
This running difference for what from UV?
Yes, the left one is from AIA 131. Yeah. And we have nice observation even with KCOR. So all these outflows that you see here are very well related to whatever the blobs we see in KCOR white light observation. So we have a ton of information about their temperature and density of these flows. So though it's little difficult to comment how they are these flows are reconnection exhaust or they are plasmoids, but we have some constraint based on their temperature and density. So far, so good. So we were going very good. We have different methods of observations from remote sensing, imaging, spectroscopy, spectropolarimetry. And then when Parker Solar Probe was launched in 2018, there was a hope that one day we will be able to probe more of these transient phenomena deeper in the corona, because Parker is going all the way up to 9.8 solar radii, which is the closest to our star so far. And in doing so, it is literally probing the corona and all the transient phenomena that we see from farther distances. We will be observing with Parker very close and probing the ambient plasma and magnetic field in high resolution, not only from imaging, which has a very wide field of view, about 100 degrees, but also with in situ measurements. And this is where things become interesting. So before the launch, these are some of the visualizations that the team prepared, that if there were a CME and Parker was flying in very close by encounter, how the things will be. And there were some tools developed by the team that were highlighted here, that what sorts of measurements to be made and how to interpret the data, because this was unlike other data sets that we are used to, like Glasgow or stereo, where things are at 1 AU and you just make the measurements. And this thing comes true on September 9th, September 5th, 2022, a couple of years back, when Parker was during its perihelion period, and it saw CME way closer than earlier, because earlier either you are seeing it from, say, some 30 or 40 solar radii distance, and but this event provided an opportunity not only to image the detailed structures of a CME, but also to observe the in situ plasma properties of the throughout its encounter. So it was like a complete dream come true moment, where what we had envisioned with this particular mission is kind of coming true. But before going further, like how to interpret this data, because our spacecraft is moving so fast, like it covers half the sun, like one hemisphere it covers in less than a day. So that's so fast, like 160 kilometer per second. That's incredibly fast. You can go and come back Denver, I think 1.5 times, something like that. And during this period, this spacecraft was connected with this spiral very close, and the CME is roughly along this arrow. And apart from Parker, there was Solar Orbiter, which had just come from Venus Gravity Assist Maneuver. Please keep in mind, this is a very important point that impacts many of the operation of Solar Orbiter, because it was just completing its maneuvering and not all the instruments were running in full cadence mode. So from Earth perspective, the source region was at the behind side, and the only instrument or the only spacecraft that was looking at the source region properties was Solar Orbiter, but with not so full cadence. So it has interruptions. That makes it interesting. So from Solar Orbiter, so this is the UV imager from Solar Orbiter, and this was the active region that led to this huge CME that Parker saw with its imaging instrument. And during this period, Parker moved all the way from about 15 solar radii to its perihelion of about 13 solar radii. And the results that I'm showing in some slides ahead are only for this time duration, where we can see the CME in the imager field of view. And I will come to these panels later again. So if we look into the UV movie, so after the eruption, these post-flare loops kept on growing, and even for about 24 hours or so. In news, this was the snake-like event was reported as the snakes on the sun, and it was one of the popular theme back in like 22. But after whatever the instability that triggered, but there was an eruption after that snake-like event. And this CME was so wide that after a couple of frames, you can see here on 5th of September around 16:30 UT, and within 6 hours, the CME has engulfed our spacecraft. So all the way we are traveling within the CME, and at the same time we had some information for a few hours. We had imaged the CME very closely before going into it. As I mentioned before, this was one of the trajectories we had never encountered before. Therefore, people have developed some tools to interpret the data. And it's not something like the CME is moving here, but CME is very close to the spacecraft here. Say Parker is located at P, and we are trying to probe something called Thomson sphere. And in doing the analysis for these kind of observations, what we know is from observers' point of view, there is an imaginary Thomson surface where the efficiency of these scattering observation, the white light scattering, is maximum, which always is defined by the sphere with diameter joining the observer and the sun. But for Parker, since it's very close, like 13 solar radii, this sphere is very small. So unlike the traditional approach where we assume the sky plane and the Thomson surface very close to each other, so in small angle approximation, the uncertainties are bearable. But imagine for Parker, this is the plane of sky for Parker, and this is where Thomson sphere is. So the distance is huge. So just assuming plane of sky approximation won't work. So we used this Thomson scattering approach, did some little bit of math and reprojection based on the geometry. It wasn't too hard, but it took a while to get the intuition how to imagine things moving all the way, like the spacecraft is moving, CME is moving, everything is moving. And then we projected everything in the polar coordinates where y-axis is distance here. So in the previous movie that we see here, so everything is in elongation angle. So the sun's 0, 0 is here, and it's just the angular span. But we do not have the information about how far we are looking in terms of the solar radii or the kilometer distance. We converted very carefully in this coordinate system. And then you can see that there was a CME, and there are some substructures, especially this cone-like structure that's moving upwards. Along this dashed line, I show here a distance time plot where this first ridge is the leading edge of the CME, this bright one, whereas the second one, the curving one inside, is the conical structure that's moving upwards. So when we measured the slope of this ridge, it gives the speed of the CME, which was like 2,500 kilometers, which is indeed very high for a CME, and that too during rising phase of solar cycle. Not many high-speed CMEs are observed during the rising phase, so this was an unusual event. And on the other hand, this the V-shaped arc that was located behind the CME is moving only at 400 kilometers per second. We verified this speed discrepancy with other imager that was available with stereo, and it's real. We don't know the cause of it, but we know that things are traveling at different speeds, like 6 times what we are seeing the difference here. So that's interesting and a question for future. Since we talked about the imaging observation, what about doing stereoscopy, like graduated cylindrical shell that we are used to do using LASCO and stereo observation and even with KCOR? But unfortunately, if you see the timestamps between the frames here, it's again 4 hours, and the CME just appeared. Then there was a time gap, as Dan always says, who is in Surrey, that whenever there's an interesting event, we get some sort of anomaly in the spacecraft and observation happens. And it happened here that there was an interesting CME. We captured it in only 1 frame, and then observations were blacked out. And remember the thing I talked about solar orbiter, it just came out from the Venus gravity maneuver thing. So METIS was observing at a cadence of 4 hours, and that 4-hour window was right when this CME would have been in its field of view. So we had only 1 viewpoint that has continuous observation with stereo. LASCO was down, METIS didn't observe. So how can we constrain more on the properties of this CME? Fortunately, we we grieved for a moment, but we remembered we had some source region information where from the UV images from solar orbiter, we can locate the latitude and longitude of this source region and approximate tilt, which are some of the basic parameters required for 3D visualization of this CME. And also, since Parker was going through the CME, we know exact time when the CME has hit the spacecraft. And knowing that exact time also gives us the coordinates at which the spacecraft was located, say, in the Carrington frame. So combining this information, like at around 1735, the spacecraft was hit by the CME, and this corresponds to about 235 degrees kind of Carrington angle. And this angle, this dashed line is the Carrington longitude for the source region. So taking this information into account to give a limit about how wide the CME is, we estimated the half width is roughly 60 degrees, and the lower limit of the complete CME is about 120 degrees. So it's pretty wide because the normal width of the CME is less than 90 degrees or 60 degrees occasionally. So it's energetic, it's wide, and that's how we fitted this GCS wireframe. And when we tracked in multiple frames in stereo on the right side, the CME speed was about 2,700 kilometer per second, further validating the estimates that we saw from the WHISPER observations from Parker. Some thoughts on the typical nature of this CME. So if we plot the speed distribution of all the CMEs that are there in the CDOC catalog, roughly 33,000 CMEs at the time of that study. So our CME lies along this red dashed line. So you can see there are only a handful countable number of CMEs having such huge speed. So this makes it one of the fastest and also one of the fastest during the rising phase. And when we looked at all the CME information that lied more than 2,000 kilometer per second speed, there are only a couple of CMEs that showed like 2,000 or 2,200 kilometer per second speed. So it makes it one of the most energetic CMEs that we have seen in last decade. And fraction-wise, it makes only 0.15% of all the listed CMEs that we have known so far. So it is a rare event on its own. And this part of the work, you can scan this QR code to access more information about more details about the imaging part. Now, let's dive a little bit deeper. On the left is the context of the different observations that were continuous during this period, obviously using JHelioViewer. On the right is again the height time map that we had made. And for this small window, we also looked at the STIX, which is an X-ray instrument on board solar orbiter. And in STIX, what we saw is the X-ray flux that was before this flare was somewhere in the lower regions. And even after the CME has passed, we can see the later part, the flux hasn't reached to the pre-flare values. And that made us think, like, what if some secondary processes are still going on? And when we were just discussing all this, we happened to see this plot, which eventually came in Orlando's paper a couple of years back, again on the same CME event. So this is an in-depth in situ observation about this particular CME. They have talked almost everything, different phases and how different parameters have changed. And you can see the span all the way from September 5th to September 7th. And based on their analysis, the spacecraft enters the CME around 17:30 of September 5th. It remains inside the CME till 12 noon of September 7th. So about 1.5 days, the spacecraft is within this CME, and it is encountering all sorts of different alvenic, superalvenic flows within the CME. An interesting part that caught our attention was the field reversal here. So the blue one that is shown here, that goes reversal from positive to negative insert a small instant of time, which encompasses like 25 to 30 minutes. And in this very small time, there is also enhancement in plasma beta and temperature. That caught our eye and demanded further investigation. Though in their work, they try to explain this scenario by two explanation. One, either this reversal, which is also current sheet, because the field is going from positive to negative. So that current sheet belongs to a CME, or there are two different CMEs, and this layer, the inversion layers, is found between those two CMEs, though they were not sure which one is the correct one. And in another explanation that came last year, they explained this reversal as heliospheric current sheet. So they didn't try to, because their argument was, since the source region was below the equator, there is very less chance that it will belongs to CME, but it's just a heliospheric current sheet that we are encountering. There was a mathematical paper a couple of years back that what's the probability of Parker encountering a CME current sheet. And as you may have guessed from the title of my talk, Parker is flying through a reconnection current sheet. Maybe I may have spoiled it already, but they have analyzed how probable it will be and what orientations are required for a CME current sheet to cross the spacecraft and detect the in situ properties. So many questions to answer. So what's the way forward? Like 10 years back, wow, it's already a decade now. So there were observations on long-lasting flares, suggesting that some of the reconnections last longer than others, meaning that we often see the flaring activity that peaks for a few minutes and then slowly decays, and like within few hours the reconnection stops. But there have been some notes in the literature, including this study by Matt West and Dan Seaton in 2015, where they saw the post-flare loops that are the giant arches. They are rising continuously, which are an indirect signature of ongoing reconnection, and it lasted for more than 24 hours. If I remember correctly, it went even till 48 hours. And you can see in this movie from SWAP that how after a M2 class flare, these giant arches kept on rising. This wasn't the very first observation, but there were observations even in, I think, 80s and 90s, which H-alpha and X-rays, that you can see some of these reconnections going on and on. So what if our case is something similar, that the reversal of magnetic field that we seen earlier is perhaps related to an ongoing reconnection? And if we look closely to our movie here, we do see that these loops are persisting in time for about 24 hours or so. So this made us think that what if it is in real related to the current sheet that we are seeing with in situ measurements around 14 solar radii, that's within the outer coronal boundaries. So we went and used some solar orbiter and Parker data in combination. On the figure here in the left, the background magnetogram is from solar orbiter phi, where red shows the positive polarity or northwards and the blue the other polarity. And on top of this, Sam Badman from CFA, he has overlaid the back mapping of the magnetic field measurements by Parker Solar Probe at potential surface about 2.5 solar radii. Though it's not an ideal way, but based on the limited tools that we have at the moment, the interesting thing, if we zoom in, is that if you look here, the polarity is going from red to blue in remote sensing, and the same polarities are measured in situ going from positive to negative. this was the first hint for us to relate these two things together, that something is going on down in the corona, and that is expanding way in the in situ data that we are encountering with Parker Solar Probe. Further, on the right are the in situ measurements from the Parker data. On the top is the stall angle of the electrons, where you can see, though I'm not an expert, but I have a very good help from in situ experts on this particular topic, that across the current sheet, we see the density going from, say, one color to other side. And within the current sheet, we will see all these spread. So you can see here the orange is spread all over the place. It marks that the field lines are still rooted into the lower corona. And whereas in the other sides, it's one of the polarities, depending on where the electrons are moving. But other things that make sense here are this magnetic field. The radial component is moving from positive to negative. And there is a current density proxy based on certain assumptions, depending on the variation in magnetic field, that there are certain peaks that are within this reversal region, whereas it's very close to base value in the regions other places. Other than that, we have the radial velocity of particles that are increasing from their base value just as the spacecraft has entered this reversal region. And at the same region, we have the temperature also rising. So all these things hints towards a current sheet phenomena, that we are indeed passing through a current sheet. And unlike heliospheric current sheet, where the speed of particles remain more or less constant, we are seeing an enhancement, though it's a few hundreds of kilometers per second, but this enhancement are only bound to this small region. So that is another hint that it's unlike heliospheric current sheet. We have a different type of current sheet, which we have certain evidences that points towards the fact that it's in fact a CME current sheet. And also, the magnetic pressure you can see is showing a dip in this region, whereas it's dominated mainly by the thermal flow pressure. So, all these things hints that we are within this current sheet region. And there was a recent paper by Fan where they studied this particular current sheet and analyzed that how energetic this phenomena is here, unlike the typical heliospheric current sheet, because they also pointed out at their conclusion that perhaps this can be the very first observation of CME related current sheet within the solar corona that we have observed with Parker. And if we look at our imaging observations, which hopefully goes well to online, it's not playing good. Performance issues. Please play. So here you can see some of the flows after the CME that looks very much structured. Like there are continuous white density structures that are moving outwards up to certain time, and after some time, which is roughly 24 hours after Parker has crossed the current sheet, it becomes more or less uniform. You don't see those many structures as you see right now here. So this was an indirect thing that we tried to interpret, like what if these outflows are again reconnection exhausts that we are seeing continuously, and after Parker has looked the other side of the current sheet, it's no longer there. So that was also one of the things that we can put back in the puzzle and get a complete picture. So we also looked at some simulation. So this is done by Cheyenne from CFA using Nirvana code, where we have a 2.5D model, and we simulated all the different scenarios, and at different cuts we measured the profile of magnetic field, speed, density and temperature to see which one best fits or which one best mimics the observation that we have, to get an idea that in what region of a current sheet we are. So here you can see the reconnection jet moving all the way in the top. Then there is a plasmoid, and then there is an X point, and this is very lower in the corona. So comparing the synthetic profiles with the ones with observations on the right, we can see that the radial profile that you see here, kind of inverted N, is what we observe here. Not only that, the speed and temperature is showing enhancement, what we see in the simulation. Unfortunately, the density was pretty messed up. You can see that it doesn't well match the starting point, though there is a dip at the later point. But again, maybe because we are using some idealistic assumptions during our simulation in ideal coronal environment. But most of the profiles suggest that we are in a reconnection jet within the current sheet and not in plasmoid or any other region. And this distance we converted based on Parker's average speed of about 150 kilometers per second to the time it traveled. And this complete jet width is about 80 megameters wide. And the individual crossing that we see here from positive to negative is about 500 meters wide. And that's also limited by the instrument resolution, because it was sampling at some 30 millisecond, if I remember correctly, or 100 millisecond, but that was very, very high cadence observation. Yeah. So it means that maybe we are not yet probing the very thin nature of current sheet. It may be even thinner than what we have measured with the Parker. And if we look at the source region, again, as I was pointing out, that these post-flare loops persist all the way for more than 24 hours. So we also know that as the loops arise, they also expand. So if we can measure the separation of foot point ribbons, we can indirectly comment on the rate of reconnection. People have done this in various studies in early 2000s. And when we see a quick movie here, and if let me put my cursor around here, and you can see that the foot point is still moving further. So this movie spans for more than 24 hours from 5th to, I think, the late midnight of 6th. So it means that we have some hint that the reconnection didn't turn off. And when Parker has crossed the current sheet, which I will just show here, so the Parker crossing the Carrington longitude is somewhere here, and this is our foot point separation that we measured by tracking the foot points manually. And this separation is still increasing very slowly, like 500 meters per second, that kind of speed. And during the time of crossing, it's still going upwards. It means that the reconnection is still going on. And this was our clue that it was indeed a long duration solar flare, and the reconnection was going on when we are crossing it. And based on some math that we did, we estimated reconnection rate to be about 0.02 to 0.05, which is in fact very high. These type of rates are generally observed when we are in just after peak phase of a flare, like within an hour of the peak flare. So imagine how fast this, or how consistent this reconnection may have been taking place. And this is the math that went into calculation of reconnection rate. Since we didn't have the direct magnetic measurements, we relied on some formulation by Sobe et al. 2002, where different forms of energy and certain approximation had gone into it. But the underlying core is that the measurements that we can make is the foot point and the magnetic field. Still, the fast reconnection rate that we get gives us an idea, or then a magnitude about how fast the reconnection is going on.
Ask you a question.
Yes.
The longitude, you said that was centered above the active region,
Yes.
right? And that 8 gals you just showed, where is that located?
So this is roughly along this region. So that's the average.
So in the heights of the AIA data.
Hmm. Yeah. So in this formulation, we try to relate different forms of energy to finally estimate coronal magnetic field using the photospheric field, which we have measurement with the solar orbital magnetogram, and that we just kind of scale it to coronal field strength at 171 angstrom wavelength. So whatever height that corresponds to. And since we were talking about the longitude, and remember this plot that I showed in the beginning, where I mentioned that this region, roughly around 300-degree longitude, is marked with this dashed line, and this solid line is actually the trajectory of Parker. And you can see that they are going to intersect at some point in time. And based on the observation and this trajectory, we see that these are within 1 or 2 hours of closeness. So it was indeed a CME current sheet, because the longitude and all the other pieces of evidence, we tried to establish that we are within the CME. And in Orlando's paper, they say that up to 7th of September, so all the way from the late evening of 5th September to 7th September, we are within the CME structure. So there are many interesting things still needs to be explored about this CME, this current sheet. But in this work, we have just established and tried to prove that this is the first observation of a CME-related current sheet that's still ongoing. Just to give a context about, even though the source region was in the southern hemisphere and the spacecraft is very close to the ecliptic plane, what kind of scenario it would have been that Parker is encountering this current sheet. So in this cartoon here, I have shown only a small portion of the field lines corresponding to two ideal cartoon that we have studied in our textbooks. But if you look closely, the source region of this CME is inclined, meaning that the loops initially are top down, and then later they have inclined to left-right orientation. And once we have this kind of scenario, we can imagine that this 2D cartoon picture that we generally draw makes it suitable so that it's perpendicular to the screen here, and hence the spacecraft is able to cross it. So this is our interpretation, that there is a part of current sheet that's curved towards the ecliptic, and that's where Parker is crossing, whereas for most of the parts, the current sheet is lying along the line that I'm trying to make with the pointer. So talking about the general reconnection scenario, it was in late 40s and early 50s when people started talking about magnetic reconnection. And in late 1950s, Sweet Parker came up with a simple model to explain how the magnetic annihilation will take place. And then in 60s and 70s, the models to explain the fast reconnection of Patrick and CSHKP model that integrated various observables that we were known back then were were developed and explained. And in last few decades, then there were other developments like turbulence-driven reconnection, and then plasmoid instability. So there were all sorts of developments taking place. And then after the launch of X-ray satellite Yoko, if I remember correctly, so some signatures were seen in X-ray in the solar atmosphere. SATs were discovered in early 2000. And during all this period, we have been observing remotely the signatures of reconnection from remote sensing instruments on Sun, whereas in Earth's magnetosphere, with MMS and THEMIS, people have been reporting the reconnection dynamics in the near-Earth environment. And then there was a current sheet magnetic field measurement by Bin Chen and his group for the September 2017 event. And now in 2022, we for the first time have crossed a CME current sheet within the solar corona. Uh, why it is important? Because Parker is flying within 16 solar radii. That's way low in the observations that we have made to date. And we are in the corona, reconnection is still going on. And most importantly, it's related to a CME. So just to summarize, we we discuss here how a very fast CME during the rising phase of the current solar cycle was observed by Parker Solar Probe, both with a combination of remote sensing and in situ measurements. Based on the reconnection rate, we conclude that it's Petrик-like fast reconnection, that it's still going on more than 24 hours. And based on the evidence from both remote sensing and in situ by combination of solar orbiter and Parker Solar Probe, we say that this is the first direct observation of a post-CME current sheet in the corona. And the width of that region, the jet region that we probed, is around 80 megameters with individual crossing of about 500 meters. And based on the simple model that we use, so most of the parameters agree very well with what was predicted by our simulations. And a preprint of this paper is available in this QR code, and we expect to have this paper published soon. So, thank you. Open for questions.
Thank you for this very interesting talk. And any questions?
So it has a fairly large latitudinal extent. Do you
Yes.
think that is normal or just because this is such a fast CME? Because if it's normal, then you can speculate how frequently one can expect a spacecraft to encounter one.
Yeah, I guess because it's very energetic and you see it is about 120 degrees wide. It can be even more than 120. It was the lower limit that we could estimate based on the data that we have. So because of such wide nature, it covers both above the ecliptic and below the ecliptic. But the phase of solar cycle that we are now and Parker going further down up to 10 solar radii, we hope to see more of at least some of the CME current sheet. Depends on how the new data release is going to be, which should be around in a couple of months, maybe.
Were there particles associated with this? Energetic particles?
Yes. Yes. There are many energetic detections both in Parker and solar orbiter data.
Your estimate of the reconnection rate is at what height?
So we estimated at the coronal height that
Not the height where the Parker is.
no.
Okay.
So we were trying to see if the current sheet that we are encountering here in the coronal heights still has got connection down in the corona.
So you used variable
Yes.
to estimate the flux.
Yes.
And then from that you calculate the electric field in the current sheet.
Not exactly electric field, but the different energies that we got here. So these energies, including conductive, radiative, and thermal, and we then equated to get the coronal energy.
Current magnetic fields.
Yes. And the reconnection rate is eventually what we are seeing, the reconnecting field at the coronal heights.
Not okay, but this is the lower.
Lower corona. Yes. Sorry, because Parker is also in corona, and it can be confusing. Yeah.
What are the scale of this current sheet? Because if we talk about the in situ measurements, there are typically 2 to 3 scales. First is about heliospheric current sheet that we talked. It's more close to like this. Then there are quasi-stable current sheet that people generally observe at 1 AU within the ICM is generally the boundary between the magnetic cloud and the interplanetary space. And the third or fourth one we call that a small scale current sheet or the kinetic scale current sheet. No, it's not been a kinetic, we know. But what is it? And the main thing that I'm not been a part of the solar field, but generally all these current sheet at 1 AU, they carry large amount of number density, proton number density with them, and people called it as a heliospheric plasma sheet. So it's usual that when it propagates to the interplanetary space, lot of particles get piled up, and that we will not see a near corona case. So what is the scale that you observe here, and at what type you just want to differentiate this current sheet?
So there are many questions in your one question. I can understand. Yeah, but that's true. Like I was not so much into in situ stuff earlier, but when I started this project, I went through the 1AU stuff as well. And as you rightly pointed out, there has been a lot of debate even using the term current sheet, because in reality, we are with remote sensing especially, we are seeing the plasma sheet. Current sheet will be very thin and embedded within that plasma sheet. So it depends on how good your measurements are, how high cadence, high resolution in terms of energy and the temporal resolution. So for this case, we are limited with the 500 meter as the minimum that we can resolve, with the distance that we can resolve with Parker measurements. If you look at Earth's magnetopause, that limit even goes to few, say, tens of meters. Yeah. So based on just looking at the data, we cannot conclude that it's heliospheric or CME.
Coexistive, yeah.
Yes, and even before we looked at the in remote sensing observation from solar orbiter, there was no way of telling that this belongs to CME, because you cannot connect all the properties. No one has seen a CME current sheet earlier. So there were a lot of speculation, and we discussed with a lot of people that what all things we can look for, especially the electron pitch angle properties. Those are one of.
You see that the electron or something in situ measurement, the electron pitch angle is clearly showing a 180-degree shift. And
Yes.
that's a prominent, we can say, not this, the previous one that's from the another paper, I think.
Oh, yes. That shows continuous complete.
Yes.
Yes.
See, there is a currently 180-degree shift in a pitch angle. So that's a major observation of this.
So yeah, so we have tried to reproduce it, but zoomed in just this small region. But you can see it's going all the way from one side to other side, and with messy displays.
This place, yeah.
Do you have any more questions from the online people? I think recently there is also a Parker Solar Probe observation of CME, I think from Whisper. I don't know if they also have this kind of like crossing current sheet.
We are waiting for the data to be public. It's still not public, yes. But I had talked to Noor, and he said this summer the data should be online. And let's hope to find more CMEs.
Yeah, it's just this observation reminds me of that very beautiful observation of the CME.
Yeah, there is definitely heliospheric current sheet that they have pointed at, but since CME is overlapping it, it will be very difficult challenge to separate if they are different or same, because seeing in Whisper is all integrated in line of sight.
Yeah, okay. Thank you. And if we don't have any more questions, let's thank our speaker again. We'll see you next week. Bye.
Thank you. It was really interesting.